All right. So I guess we can just get into it. So last lecture we talked a bit about Cauchy transforms and how using orthogonal polynomials we can calculate them very effectively and very accurately, even up to the branch cut. And now we're going to see how we can use that for solving Riemann-Hilbert problems numerically. So this is sort of part 3, RH problems. So we have some contour, gamma, and on this contour we're given f and g. Find phi that was 1 analytic off gamma, 2 phi of infinity is equal to identity, and then 3 satisfy the jump condition, phi plus of s minus phi minus of s. We're actually going to, minus g of s is equal to f of s for s in gamma. Okay. So we want to find a function analytic off a contour that satisfies this relationship between the left and right limits. So here, for any point s on the contour, we have phi plus of s, which is the limit from the left, and phi minus of s, which is the limit from the right. Okay. So now, last lecture we talked about Cauchy transforms, and in particular Plumage, and we said essentially that any function that's, for the most part, any function that's analytic off a contour and decays at infinity can be represented in terms of the Cauchy transform of its jump on the contour. Okay, so this sort of gives a natural ansatz for phi. Well, we don't want it to go to 0 at infinity, we want to go to identity, so we write it as identity plus Cauchy transform v of z, where this is unknown. Okay, so now we can plug this into the, so this will immediately satisfy property 1 and 2, and all we're left with is property 3, that it satisfies the right jump. And now we just plug this ansatz into this to turn the jump condition into a singular integral equation. So plug into property 3, and we get, what do we get? We get I plus C plus V of S minus G of S. Is there any longer chalk? Minus G of S, C minus V of S is equal to F of S, or equivalently, we get C plus V of S minus G of S, C minus V of S is equal to F of S plus G minus I. Okay, so this is a linear singular integral equation for V. Okay. Now, for whatever reason, people always like to write integral equations as sort of identity plus something else. So then we can also use, so if we really wanted to do that, we don't really need to, but we can say use C plus minus C minus is equal to identity. So this comes from Plumage. The limit from the left minus the limit from the right gives us back F to get, so now we can replace C plus V of S with C minus plus I. And we get V of S minus G minus I, C minus V is equal to F plus G minus I. Okay, so a nice singular integral equation that involves the limit from the left of the Cauchy transform. So now how do we how are we going to solve this numerically? Well, so we're going to solve it numerically by discretizing. And let's discretize this by writing V, or approximating V by a expansion in a basis. Okay, so I'll say these are unknown. Well, if this is a matrix problem, D by D matrices. So this is assuming that F and G are D by D. Okay, where this is well, I'll just be explicit. This is piecewise Legendre polynomials. What I mean by this is if these are finite segments, we can map them to minus 1, 1, and we use sort of piecewise mapped Legendre polynomials. Okay, and provided the maps are either affine maps, Mobius transformations, or one of the other maps, polynomial maps, or the Llewellyn-Smith's Luca map, these sort of maps where we know how to do change of variables. Okay? So now for these bases, we know, let's call it LV of S. LV is either that or equivalently this, they're the exact same thing. So this is our operator. We know L in this for this approximation exactly. So we know, maybe I'll call this let's call this whole thing Vn of S. So we know LV of S, which is just sum from k equals 0, m minus 1 vk, L psi k of S. Well, this is just sum of k equals 0, m minus 1, vk psi k of S minus g of S minus I, c minus psi k of S. we know how to evaluate this for any s in gamma. Or rather, I should say, we know how to evaluate L psi k. We can essentially evaluate this exactly for any point in gamma. Okay? So how do we choose our unknowns? Well, let's just impose that this singular integral equation is valid pointwise. So choose a grid so choose n points in gamma so this is say S1, S2, S3, dot, 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 up to Sn. So we choose some grid on our contour. At this grid, we can evaluate our basis essentially in closed form because it's built out of orthogonal polynomials and because we have these mapping formulas and because we have these recurrence relationships. And then we can just solve n by n collocation system. These are our unknowns. Okay. This is for j equals 1 through n. This gives us an n by n. Well, I guess if these are d by d matrices, so in the scalar case, it gives us an n by n matrix. I guess in the matrix case, it gives us, well, it's a little bit more complicated, but it's essentially the same thing. Okay, so we solve linear system to determine okay. So then once we have Vk, these are our new, Vk tells us our approximation to V. These constants Vk tell us approximation to V. We know how to evaluate the Cauchy transform of Vn exactly. That gives us an approximation to psi. Okay. Okay, so this is all pretty straightforward. And on a single interval, we're sort of done. So maybe just before I move on to cases with junction points, let's just see this in practice. So this is just, I'll just use the lecture notes instead of trying to type it by hand. I guess these will be made available at some point. So what are we doing here? We want to solve a Riemann-Hilbert problem on -1, 1. Here we're creating a set of n points. Here I'm making up some jump g that at the left and right endpoint is numerically the identity. So this is a scalar case. Now we need to construct this matrix that's corresponding to this linear system here. That consists of just applying the singular integral operator, which is Cauchy transform of our Legendre polynomials evaluated at s with the minus limit times g minus I times pk of s. So this is literally just v of s minus g minus I times c minus. This creates this m by n matrix corresponding to evaluating the spaces at the grid. We say backslash for solve. Here f is just 0. This says we're interpreting these coefficients as Legendre, and then we can evaluate the Cauchy transform exactly. Okay. And this is, and then, so the only thing missing is what happens with Cauchy. That's where all the recurrence relationship stuff is sort of hidden. Okay. And this is exactly what happens, and so then we can test. It satisfies the jump to 16 digits, and so on, and we can see that, so this is exactly what happens when we call RHsolve. It sets up that linear system and solves it. Okay. And without any sort of further modification, it works for the matrix case as well. Okay. So at least in the scalar case, when you have a scalar and matrix case, when you have a single interval, everything proceeds straightforward. Now, what goes wrong, or maybe I shouldn't say goes wrong, or why is it more complicated when we have junctions? So now we're going to consider junction points. Okay. So let's start with splitting. So here's a very simple example, splitting one interval in two. So if we take our -1, 1, which we showed right now that we could solve on the interval simultaneously all at once, and add in a artificial junction point at 0, okay? So now instead of using Legendre on the whole thing, we're using Legendre on each of these intervals separately. Well, the issue is, is consider just the first element of our basis on this interval, which has this form. Okay? The issue is that at 0, it blows up. So, and similarly, this term also blows up at 0. So if we just split our interval into 2 and solve for coefficients without being too careful, we're going to get a solution that introduces an artificial singularity where we put the junction point. Okay. Okay. What I want to say. Okay. So how are we going to do this? How are we going to get our collocation system to ensure that these logarithmic terms that naturally appear when you split one contour into separate ones, how are we going to ensure that the logarithmic terms cancel? Okay. So, to make them cancel, we're going to actually include the junction point in our collocation points, but repeated once for each adjoining contour. So maybe let me introduce some notation to sort of make sense of this. So, so there's something called a dual number, which is algebraically, you write it like this, where epsilon is thought of as infinitesimally small, and algebraically it satisfies the property that epsilon squared is equal to 0. So this is equivalent to thinking of it as this matrix, because if we think of this as A times identity plus B 0 1 0, if this is epsilon, this squared is equal to 0. So we could compare with A plus IB, which is equivalent to A B minus B. Okay, so just as complex numbers can be thought of in this matrix version, we can do the same thing with dual numbers. Okay. So I'm just going to mention, because because of machine learning, automatic differentiation is becoming more and more important. I'm just going to mention briefly that these are important for automatic differentiation because if you have, say, an analytic function and evaluate it on a dual number, which is equivalent to matrix function evaluated on this matrix, you get out the derivative. So evaluating at a dual number is a very convenient way to evaluate derivatives. And let's say you have a very complicated function f of g of h plus, so like gamma of gamma of gamma plus cos or whatever, some very complicated function that's hard to differentiate symbolically. As long as you define it for a dual number, you can get out the derivative essentially for free. So this is sort of the most basic example of automatic differentiation. Okay. So, but we're just going to really use it for, if we think of B as complex, we can use this tool, which is very useful for software. So the point is, on the software level, you just, as long as, for example, gamma function is overloaded for dual numbers, then you can differentiate gamma functions and compose functions involving gamma functions or whatever. We're going to just use that idea along with the fact that if we make B complex, this gives us a convenient way of assigning an infinitesimal direction as we approach, say, a junction point. Okay, so now, so back to our collocation system, and now we have, say, a junction point. And let's just think of this as a union of three contours. And let's say this is at angle theta 1, angle theta 2, and angle theta 3. What we're going to have in our set of collocation points, S1, S2, S3, we're going to have sort of 3 points, all at the junction point, but corresponding to this epsilon angle. So this is, so let's assume the junction is at 0. Then we have 3 points, which is epsilon, it's that infinitesimal version of epsilon there, epsilon e to the I theta 2 and epsilon e to the I theta 3. Okay. So now we have 3 collocation points, or for example here we could have, say, epsilon and minus epsilon. Now we have our basis evaluated at this. Now log of z blows up at 0, log of something infinitesimal also blows up. So, but as a bookkeeping device, we're going to introduce, and this is just a formalism. We're going to introduce just a formal notation, which is log of b epsilon is equal to, well, I'll just write it as a plus b log epsilon. This is just a formal notation where we capture the fact that there's a constant term plus b times something log of something infinitesimally small. And then you have log of b epsilon is, of course, just log b plus log epsilon. Okay. Okay, so this is just a formal device which is useful on the software. It's more useful on the software than the mathematics. On the mathematics, this is just equivalent to saying the limit as z approaches 0 has this behavior. This is but this is useful on the software because software you can't really encode limits, but you can encode special data types like log numbers and dual numbers. Okay, and note that the definition of what you get depends on the angle of approach. The constant term is sort of theta dependent. Okay, so on the software side, if we implement log, for dual numbers and multiplication, addition for log numbers, what does that buy us? This means that on the software side, we can evaluate Cauchy transforms at epsilon because you plug it into the first moment. This gives us log epsilon minus some constant. That's a nice log number. But then you can also do the recurrence. So on the software side, you sort of have 3 lines, and you can evaluate Cauchy transforms where they blow up and make sense of the result. So it's factored out the constant part from the log term in such a way that when we add things together, they cancel out. Okay. All right. So I think okay, so So back to the collocation system. Here, we're assuming we have a junction point in our collocation point. We evaluate our basis at that junction point, one time for each edge. It blows up, but we capture that as a log number. And what we do is just throw out the log part and impose another condition so that these log parts are guaranteed to cancel out. Okay, so let's write it explicitly in terms of this this 3 gamma case. So we have 3 conditions. We have sum from k equals 0 to m minus 1, vk psi k 0 is just the junction point. Sorry. Theta 1 is equal to whatever the right-hand side is. Okay, and then we have the same thing, but epsilon e to the I theta 2. But then instead of imposing the third one, we can replace that by what's called, by a condition that ensures that all the logarithmic terms cancel out. So what condition is that? That is simply that simply that, so this is condition 1, is just Vn epsilon e to the I theta 1 plus Vn epsilon e to the I theta 2 plus Vn, just a sum of our unknown sum to 0. Okay. Okay. So we're writing our solution as a function v defined on gamma. If the limit as we approach the junction point, if these 3 limits sum to 0, we're guaranteed that the logarithmic blow-up gets canceled out. And by adding this to our system, we can impose that condition explicitly, in which case here, this was some log number, but we just ignore the log part and take that as our definition. Okay, and that gives us an n by n system that imposes this, what I'd call zero-sum condition, that ensures that the log terms cancel out. Okay. So I think there's some more detail in the notes, which I guess will be posted, but maybe I'll stop there and move on to the next topic. But at least that gives a hint of how the numerics works, including when you have junction points.
Question.
Yep.
I may have missed it, but what restrictions are there on G? Can it be singular at a junction point, etc.?
Right. Okay. So. Okay. Conditions piecewise, I'll just say smooth, but obviously that can be weakened, where here the pieces are everywhere apart from the junction points. 2, there's something called the product condition, which is, I'll just write it for the 3-1 case, but the generalization is obvious, is that G3, G2, G1 is equal to identity. Here I mean G3 is just the value as we take the limit along the corresponding thing, G of epsilon e to the I theta 3 and so on. Okay, so we need the product of all the jumps to be identity. And there's the third one, which we call the cyclic junction condition. So this is a condition on, so assuming we have the product condition, this is a condition on the right-hand side. So I'll use R, which in this case is F plus G minus I. Okay, and this condition is again, I'll just do the three contour case. Okay. So if we don't have an F, note G minus I satisfies 3 if 2 is satisfied. So anytime we have something that satisfies the product condition, the right-hand side, if we don't have the F, the right-hand side automatically solves this condition. And that's a simple telescoping sum. You just plug in G3 minus I, G2 minus I, they cancel, and so on. Okay, so provided our right-hand side satisfies this condition, and the jump G satisfies this condition, we're sort of guaranteed, assuming the Riemann-Hilbert problem is well posed, it not necessarily is, but assuming it is, that we're going to have piecewise analytic locally near the junction. Okay, so hidden in this is this condition, and then this condition is also used to sort of verify that what we're doing is correct, but I think it's getting a bit heavy. Okay. Okay. Yep.
All numbers, is it basically the complex approximation when you look at derivatives?
The what?
You can work out a derivative approximately by taking the imaginary part of x plus h, say, divided by h, as opposed to like a standard limit.
Right. I mean, it's morally the same. Yeah, I know what you mean, where you use a complex step to approximate derivatives. It's morally the same. I'm not sure if it's actually, is it literally the same?
I just wonder if there's a scaling with
The scaling with, no, so that's the difference, is that when you do the complex step, you need to put in like in a computer, you have to put in like an epsilon perturbation.
Right. Yeah, okay.
Here it's just, for example, if you, so if you have a function defined on a matrix, you can do sort of just plug in the matrix and the derivative will come out essentially to machine accuracy. So it's, but okay. So I'm going to sort of for the most part, stop talking about the numerical side of things and move on to the last topic, which is sort of a standard technique. Well, we'll see how it applies is useful for numerics at all, but it's a standard technique for dealing with oscillations in the Riemann-Hilbert problem. So it's called Dice-Style steepest descent. Okay, so let's go back to, we had 3 examples. One of them was NLS, which had this sort of, it only had a jump on the real line. It had a very simple form, 1 minus absolute value r squared. Minus r bar. This is a function of k, or I think I was using s. I'll just write theta of s, r e to the I theta of s, and then 1, where theta of s is 4t s squared plus 2x s. Okay. So this is supposedly something not too far away from what comes up in Wiener-Hopf problems, matrix Wiener-Hopf problems. This is coming from the integrable system side of things. It's looks fairly simple. The complication is when t or x become large, and this corresponds to evaluating the solution to NLS in the tx plane. This becomes more and more oscillatory. Now it stands to reckon that the solution is, if the jump is becoming oscillatory, the solution is becoming oscillatory. And to capture oscillations with polynomials, we need more and more coefficients. So on the numerical side of things, as x or t become large, n needs to go to infinity. Even worse, the linear system, the collocation system, is ill-conditioned. So as x and t become large, it's not just bad. It's actually horrible, because it takes very long time to solve, and the answer it gives is very inaccurate. Okay. Now, Dice-Style steepest descent gives a way around this, and it was originally was developed in terms of asymptotics. So the question was, how do we solve, for example, how do we calculate long-time asymptotics of NLS? Or Pan-Levy, or any of these problems with oscillatory Riemann-Hilbert problems. But the same tool is also useful for numerics. So, called steepest descent, you can sort of guess where it's going. We have something oscillation, oscillatory. We want to turn it to something that's exponentially decaying by deforming in the complex plane. Okay. So our idea is to form the RH problem. This is not the same as integral deformation in the complex plane. So how do we do this? So let's say, here's our jump, but we want to deform it to this contour. Okay. So let's call. So we have a jump here. We want to deform the jump there. Let's just label these regions. Say omega 1, omega 2, and then I guess there's only one omega 1 as I've drawn it. Okay. So let's define a new unknown as so here we want to solve phi plus equals phi minus g. I'm going to use the right version of the Riemann-Hilbert problem. We want to deform it to 1 on the red line. Let's do a change of variables, and inside omega 2 we do phi define equal a new unknown psi times psi is a new unknown, which is just phi times C inverse, G inverse. And outside, so in omega 2, psi is defined as phi times G inverse. In omega 1, we just have psi is phi. Okay, so assuming our jump can be analytically continued, or in particular G inverse can be analytically continued into omega 2, this defines an analytic function in each of these regions. So what does it solve on? So what jumps does psi have? So here on, let me make it red. On this red line, it satisfies psi plus, so that's in omega 1, is just phi, which is just equal to psi minus times g. Okay? Where here, on the old contour, it satisfies psi plus is equal to phi plus times g inverse is equal to phi minus g inverse is equal to psi minus. Okay. So what's the conclusion? The conclusion is we can just deform, using the simple change of variables, we can deform a contour in the complex plane provided our jump is analytic. Okay. So can we deform our NLS in the complex plane to turn the oscillations in e to the I theta and e to the minus I theta into exponential decay? And anyone see the problem? Well, there's two problems. So we want to turn, what happens to e to the I theta if we deform it onto the path of steepest descent? Well, if we deform the contour so e to the I theta decays, then e to the minus I theta blows up. Okay. There's a less serious issue, which is our bar is not analytic, but I won't. This really just means R bar of K bar, or S bar. Okay. So R bar can be made analytic. That's a very minor issue. R is something like the Fourier transform, so it's going to be analytic in a strip. But then we want to deform this to turn oscillations into exponential decay. So fortunately, there's another trick that allows us to decouple the e to the I theta from the e to the minus I theta. And this trick will allow us to deform one sort of in the upper half plane along its path of steepest descent, and the other in the lower half plane to its path of steepest descent. And this is called lensing. So if this jump can be written as, and this is something that I guess everybody here will like, as a matrix factorization. Well, unlike the sort of classical Wiener-Hopf stuff, we're not assuming these are analytic everywhere in the upper half plane. We're just going to assume they're analytic in a neighborhood. Then we can take our single contour with G and split it, essentially the same trick as there, into 3 jumps, A, B, and C. Okay. So this is very just very similar to what I wrote before. We just say psi is phi outside of here, and then in there it's going to be phi times C inverse, and then in here it's psi is phi times A. So provided that A is analytic in this region and C is analytic in this region, we're allowed to do this. Okay. So then the goal becomes to find a matrix decomposition for our jump G, so that we can sort of split the e to the I theta from the e to the minus I theta. So here we have, and for whatever reason, these always turn out to be sort of very basic decompositions. So what matrix decompositions do people know? There's LU decomposition, there's UL, there's eigenvalue. It turns out you never need eigenvalue in this setting. So basically we just need LU, UL, PLU, these sort of variants of standard linear algebra. Okay. So for NLS, we have 2 ones that are useful. One is the UL decomposition. So this, I'll just write down the jump really quickly. I probably forgot an I, didn't I? Oh no, I didn't forget an I. Okay. Well, we can write it down as a UL decomposition. Okay? So if you multiply those 2 matrices, you get the original G. But it's done the effect of putting the minus sign. This matrix only depends on e to the minus I theta. This only depends on e to the plus I theta. So therefore, if in this case B is just identity, if this decays in the lower half plane, we're in good shape. If that decays in the lower half plane, this one decays in the upper half plane. Okay. Well, it turns out in this case this isn't enough. We also need the LDU decomposition, which also is pretty simple. Okay. Which you could just work out by Gaussian elimination, but whatever. Okay, I forgot to mention, when I say absolute value r squared, I really mean r times r bar, where r bar is, so maybe I should write that so that people don't get angry about me saying absolute value r squared is analytic. Okay. So this is L, this is D, and this is U. Okay. So let's call this L, this D, this U, And then the convention is to call this one M and this one P. Okay. So depending on whether we want decay in the lower half plane for e to the minus I theta or e to the I theta, we're in good shape. Okay. Assuming that R is analytic, which we know it is in a strip, and assuming that this doesn't blow up, which we can actually guarantee, but that's sort of outside the scope. Okay. So then, So now we want to figure out what the paths of steepest descent are. And just like classical steepest descent, the first step is you find the stationary point of theta and try to deform through the stationary point, because that's going to be where the paths of steepest descent are. Okay. So in this case, it's just theta prime of S is whatever it is, ATS plus 2x implies theta prime at I guess minus x over 4t is equal to 0. Okay, so let's call this okay. So now I'm going to take for granted everyone here is comfortable with standard steepest descent. We take our original jump g, which is posed on R, find this stationary point, Z0. All right. Then you think, where is e to the I theta decaying? Where is e to the minus I theta decaying? And based on that, we choose either the UL or the LDU decomposition. So in this case, to the right of the stationary point, we want the UL decomposition, and to the left, we want the LDU. Okay. Now, from other properties, essentially Fourier transform-like arguments, there is some strip where R is analytic. So there is a strip for so this comes from an initial condition to NLS. Provided that decay is sufficiently fast, we can ensure this R is analytic, and also 1 minus R bar doesn't vanish in some strip around the real line. Here's our point Z0. We now use the Lenzing argument to deform along contours that are along the path of steepest descent. So being a quadratic stationary point, it looks like an X, just like standard steepest descent. But we don't go all the way off to infinity because we want to stay in the strip of analyticity. Okay. So we get a jump like this, LDU. Okay. Now, as x or t become large, things become more and more localized near the stationary point, and we can then start sort of truncating this. And so so that's where the asymptotics comes from, but that's also where accurate numerics comes from, that we can then rescale it and sort of do numerics very accurately for arbitrary x and t. Okay, but I guess one key point is we started with something, a Riemann-Hilbert problem posed only on R, and we ended up so with no junction points, but due to these due to its oscillatory nature, we needed to recast it as a Riemann-Hilbert problem on junction points. So junction points are important not just when our problem is opposed with junction points, but they can arise naturally from trying to get good, well, both asymptotics, but also good numerics. Okay. So fortunately, I've run out of time to say anything about the Sommerfeld radiation, but it sort of follows from what we have already covered, which is there we have a Riemann-Hilbert problem, but with 1 over square root x decay. But we know how to map that to minus 1, 1, and write the Cauchy transform of the map basis exactly, and therefore we can set up a collocation system. And I think that's essentially what you and Stefan did. I just, maybe this...
Can I ask a question about this, what you just
Yeah.
said here, the junction point? So if your strip is very narrow because of constraints on the problem,
Yeah.
then you have to, your steepest descent is only going to work suitably far.
Right.
So it limits the numerical usefulness of
So
it.
I'm sure you already appreciate that it doesn't limit the asymptotic result.
No.
So that's, but you're correct that it will at the very least require more. So you can always make these close. The numerics will still work. It just means you have to take more and more collocation points. So you have that degree of freedom of increasing n till you have convergence. I will mention that I'm pretty sure I know how to do this without doing any deformation in the complex plane, but I haven't put that all together. Because essentially, I think you can collapse this to what I would call something more like a stationary phase type thing, but
That's what I was going to suggest, the stationary phase argument.
yeah.
Can I do that numerically, which is, I know it's not.
So it all comes down to calculating Cauchy transforms of oscillatory functions. So by deforming, we turn Cauchy transforms of oscillatory functions to Cauchy transforms of non-oscillatory ones, which then polynomials make sense. I think it's possible to do it, but we're not quite there.
Presumably, yeah, if you take your collocation spacing right for the sort of oscillatory phase, then you can get rid of all that clutter and most of it disappears, and you do it sort of cleanly.
Yeah, so there's this like, maybe someone here knows better than I do, but there's some like, there is some statement that C minus F e to the I omega x. So something simple like this, yes, we can do it without deforming in the complex plane. I think Tom Trogdon had a paper doing this, and the cusp of it is that you can, I'm going to be hand wavy because I don't remember, but this roughly looks like f e to the I omega x plus some nice operator. Okay, so then if you use sort of a rational, if you conformally map the real line to the circle, you can actually write down for that basis this exactly. And then I think he was using some iterative scheme to then solve this oscillatory Riemann-Hilbert problem. So it's, in theory, there's stuff there. For something like this, it becomes more challenging because it's not just e to the I omega x. It's more like e to the I omega x squared. So then you need to come up with a basis. So the challenge is calculating Cauchy transforms really, in such a way that you capture the oscillatory nature of them precisely.
Are there any other questions? Can I ask a question?
Yeah.
So in many problems the geometries might have exponentials and also these gamma square root functions.
Yeah.
So could you comment on what happens if, in addition to the oscillator behavior, we have branch cuts in the complex plane? How we would deform the contour there?
Well, I mean, you just have to, so the rule is you can deform this as long as you stay in the region where U, so this part where U is analytic. So you would just have to, so if there were, say, like a branch cut there, you would have to do something like that. Yep.
Is there a systematic way of doing these factorizations, or is that
Gaussian elimination?
and that works even when you've got functional entry?
Yeah, this is just, so,
The exponential factors get in the right place even if you've got lots of them for an n by n matrix. That will still follow through, or?
yeah, so, Volker Rudderman had a PhD student, George Ruschelberger, that made an automatic system that, so this is a very simple case. These things actually, the deformations become quite complicated when you, especially if you talk more than 2 by 2. He came up with a system that automatically deformed the deformations, but also had like a catalog of different matrix decomposition, and would just check every one to see which one, which one worked. And so, in some sense, it is automatable. I am oversimplifying a bit because you can also do this stuff when you have degeneracies, say when r bar is equal to 1, but then it becomes a lot more complicated because you need something that's, it's called like a g function. So, so you need to do stuff like, for example, for Panel Bay 2, our theta looked like 4/3 z cubed plus x z, and then I think you can rescale things so you get something like this. There's a very similar case where R is very similar to this, where if you imagine R bar is equal to 1, you have a 0 in the 1-1 entry, you can't do an LDU decomposition. It turns out for asymptotic regions, there's sort of no other simple decomposition that works, and then you have to do things a lot more complicated by sort of replacing theta by a g function, which looks like 4/3 z, I think 1/√2, something like that, where whatever this term is chosen so that it's asymptotic to theta of z. So you have to sort of will out of nothing a function with a branch cut that looks like theta, and then you do sort of a change of variables of the form e to the I theta minus g, e to the minus I theta minus g. So this goes to identity at infinity, and that sort of then somehow fixes the problem. So there are quite, for easy problems it's easy, but not every problem is easy, I guess.
So yeah, another place where this g function comes up is with polynomials.
Yeah.
And finding this g function is often difficult. So have you ever tried?
Well, I have a paper and software for calculating. For orthogonal polynomials, it's the equilibrium measure.
Right.
You can, so that's like a nonlinear Riemann-Hilbert problem where you don't know the support.
So you can do it. Well, what I'm asking is, can you do it on the not? Can you use the g function to normalize the problem, so you can solve things with Cauchy transforms, for instance?
Yeah.
But so you're saying there is also software out there to directly apply it on the non-normalized problem.
On the what?
On the non-normalized problem, so where you maybe have low.
Oh no, so that you use a g function to do the same thing that you do in asymptotic analysis, but you can calculate the g function numerically. So that, yeah, maybe there's not time to explain what that question was, but essentially you can use this for calculating the asymptotics of orthogonal polynomials. Orthogonal polynomials can be recast as a Riemann-Hilbert problem, and this kind of stuff is sort of essential, where